All right, here we are, last day of notes for trigonometry. Hopefully at this point you have returned to me at school, but in case you have not, here we go. Real world applications. So the height of a yo-yo above the ground can be well modeled using the equation here, where h is the height of the yo-yo in feet above the ground and t represents time in seconds since the yo-yo was first dropped from its maximum height. This is a cosine, so it does start at the maximum. Answer the following questions and then sketch a graph of the model below, including scale and label on your axis. So determine the maximum and minimum heights that the yo-yo reaches above the ground. Show the calculations that lead to your answers. So max and min heights is the range, pretty much. So you're going to take your amplitude, positive amplitude, negative amplitude, excuse me, add them together with your C value all the way there at the end. And we get 0.5 and 4 is our range. So max is 4 feet. And then min is half a foot. So, part B, how much time does it take for the yo-yo to return to the maximum height for the first time? So again, we're dealing with cosine. So we're looking for one complete cycle of the cosine curve, which means we are looking for our period, which again is the formula 2 pi over b. Our b is right there in front of our t, so our b is a pi. Divide those, so that means we get 2, and our units would be seconds. So it takes 2 seconds for the yo-yo to go down and then back up again. And then the other part of this is it did tell us up here to sketch a graph. So here's my graph. Min is 0.5, max is at 4. Midline at 2.25, because again, that's where my C value is. My period is 2 seconds. So 2 divided by 4 means that my key points are at the halves. So 1 half, 1, 3 halves, and 2. So there are my key points there. So it's going to be high, 0, low, 0, high. Always following that pattern. So there is the sketch of our graph here. Let's take a look at number 2. So the peak demand for water in a certain town occurs in the summer months and can be modeled by this function given here, where W of t represents the number of cubic feet of water needed for day number t. Assume that t equals 1 corresponds to June 1st. Graph one complete cycle for this water usage and use the graph to answer the following questions. Okay, so I got an amplitude of 1600, C value of 5000, excuse me. So to figure out, well, got to figure out my high and my low. So my range, negative 1600, positive 1600, plus 5000, plus 5000, 6600, and this one is 3400. I'll have to put a break in my graph. 3400, 6600. Right in the middle of that, my 5000. Other things we need to figure out in order to be able to make our curve would be our period. So period is going to be 2 pi over b, which is pi over 90. Do our keep change flip and we get a period of 180. Key points, 180 divided by 4 is 45. 45, 90, 135, 180. There's the key points on my graph. So then to actually create it, again, this is sine. So this is going to start at 0, high, 0, low, 0. So there is our curve W of T. So what day is the demand for water the greatest? That is going to be on day 45, which if you count it out, starting at June 1st, that makes it on July 15th. How many cubic feet of water are needed that day? 6,600 cubic feet of water. When will the demand for water be 5,800 cubic feet? So 5,800 is going to be about here. So you're looking for this number, and you're going to look at that number. There's 2 times when it's going to be 5,800 cubic feet. So in our calculators, we want to use our sine equation. And then your y2 is going to be your 5,800 like we've done before, because we're trying to figure out where they're going to intersect. So we'll go to our calculator. 1,600 sine of pi over 90. And then x plus 5,000. And that's going to be a 5,800. So I am I am going to have to change my window for this. So I want my window to match what I just drew on my paper. So my x min is 100, my x max was 180. I'll pick a random number, let's go by 20s. So then for my y min, the 3,400. My y max was 6,600. You could go beyond them, or you could hit those ones exactly. And I'll have my scale go up by 150. I don't know why I picked 150. I just picked 150. Does not matter. So then let's take a look at our graph. And there we go. That's the same graph we drew. Our midline going right across the middle there. So again, we're looking for these 2 points where they intersect. So second, trace, intersect. And we'll move my spider guy. He's closer to this one, so I'm going to do this one first. Enter, enter, enter. Excuse me, x equals 75. Pause the video. Go find the other one on your own. Should be x equals 15. So on the 15th day and on the 75th day. So that would be June 15th. Let's see here. July 15th. So 75 would be August 14th, because July has 31 days, not 30. So it wouldn't be on the 15th, it'd be on the 14th. Regressions. We can do regressions also with our sine cosine curves. It's a sinusoidal regression. So we're going to be always using the sine regression that is in our calculators. So there's 2 things that's going to happen. Sometimes your period is unknown. And that's like our first example here. We have the temperature of a chemical reaction changes during the reaction. The temperature was measured every 2 minutes, and the data is shown in the table below. We don't know how long this reaction is going on for. There is no end point. We don't know when it starts repeating the pattern. We don't know really much of anything yet with it. Our time, though, is equal increments, which is important. You need to have equal increments when you are dealing with an unknown period. So let's put that little note on there. X values need to be, that's not the word be equidistant. When period is unknown. Okay, so that's key thing number 1. If we take a look at our range values, though, it goes up, 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 down, 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 up, back up, back up. So it's going up, down, up, down. So it is going to be a periodic function. We're going to use sine for it. So if we start to go into our calculator, go to Stat, Edit, go ahead, type in your numbers. Time is your L1, temp is your L2. All right, so all of my numbers are typed in there for my L1 and my L2. So again, we are doing a sinusoidal regression. So Stat, Calc, I'm going to go up because sine regression is towards the bottom there, so you want the limits of sine reg. Reg always stands for regression. We hit enter and we get this. And you're like, oh my God, what are iterations? An iteration just means how many times the pattern is repeated. We don't actually know how many times the pattern is repeated, so the standard fill-in for that is 3. So leave that as 3. This should be L1, L2, and leave your period as blank. So 3, L1, L2, blank. That's what your parameters are going to end up being. So, low down to calculate, hit enter. There is my sinusoidal regression. Let's look at our questions. Why does it seem like this data might be periodic? Create a quick scatter plot using your calculator to verify. So, because y values increase, then decrease, then increase. So because they keep going up, down, up, down, up, down, it is sinusoidal. So let's write our equation and then we'll go back and do the scatter plot thing here. So 3.9 sine of 0.4x minus 0.7 plus 38.5. They told me to round everything to the nearest tenth. Here is your basic equation. If you look at your calculator again, these are your values rounded to the nearest tenth. Quick review on how to make a scatter plot. You would hit secant, y equals, go into plot 1 and actually turn it on. And then everything else should be set up correctly to make a scatter plot. You want the first one. Those other things in there are not scatter plots. L1, L2, you can use whatever mark it is you want to use. It really does not matter, and whatever color you want to use. And then go zoom, number 9 for stat. And so you can even see the points are going up and down, up and down. So it is sinusoidal. There's our equation for it. According to this model, looking at C here, according to this model, what is the range in temperatures in the chemical reaction will include? So just like we were doing, negative amplitude, positive amplitude, plus your last value, the midline. So that gives me a 34.6 to a 42.4. So that is our range of values. And then the period, because they want to know how long it takes to complete one full cycle. One full cycle is your period. So 2 pi divided by 0.4, which would be 5 pi or 15.7 minutes. You do want to make sure you're in radians for these. Now switching pace, when period is known. So slightly different. Maximum amount of daylight that hits a spot on Earth is a function of the day of the year. Taking x equals 0 to be January 1st, daylight in hours was measured for 12 different days, and they were random different days. The measurement was the number of possible hours of sun from sunrise to sunset. Now the parameters are going to be a little different this time because we actually know the period. We're talking about a full year. So how many days do we have in a year? 365. So after 365, it's going to repeat its cycle. We know what this period is. It has a natural period to it. So when we are doing our regression, we're still going to have 3 L1, L2, but then we would put in a period value this time of 365. So go ahead, type those values in. Day is L1, daylight is L2, and then start doing your sine regression. Okay, so here we are. Typed in my numbers, went to do my sine regression. So again, iterations of 3, L1, L2, and again, I know my periods. I'm going to put in my 365. and then I'm going to hit calculate. So here are my numbers to be able to write my equation. So natural period again for this one is 365 because it's talking about the days of the year. So our equation, it didn't really tell us where to round to. So I'm going to go to the nearest hundredth, except for my b value. I'm going to go to the nearest thousandth just because it's such a small decimal. I want to make it a little bit more accurate. And the other ones I'm going to keep to the nearest hundredth. So, what is the maximum number of daylight hours predicted? So I got to find my max and my min, just like I normally would. So 15.29 would be my maximum daylight hours based on this period. So, last thing for us to take a look at would be reciprocal functions. So let's go to that last page there. Take a look at our reciprocal functions. So consider the function y equals secant x. Remember, secant is the reciprocal of cosine, so secant x is the same as 1 over cosine x. So the graph below shows the basic cosine curve in dashed. So I drew that already. Dashed lines, basic cosine curve. So what values of x on the interval of negative 2 pi to 2 pi, which is what this graph is cosine equal to 0. So circle these locations. 0, 0, 0, 0. So negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. That's when the cosine graph is 0. What will be true of the secant at these values of x? Draw a dashed vertical line at these values. So secant, remember, is the reciprocal of cosine. So if cosine's value is a 0, we could say it is 0 over 1. If I flip that, I get 1 over 0. We can't have that. You can't ever be over 0. So whenever cosine is a 0, that means your secant is going to be undefined, which is going to create an asymptote. So we're going to have asymptotes at those 4 values. So using your calculator, sketch a graph of secant x on the grid. As a suggestion, have your calculator graph both secant x and cosine of x. Excuse me. So if I go to my calculator, go to my y equals, I first have to turn off my stat block. Otherwise, it's not going to graph anything. So I'm going to put in there first cosine of x, and then I'm going to do 1 over cosine of x. And then I'm going to hit zoom, trig, and then it's going to create my graph. So remember, my blue one is my cosine. So here's my blue basic parent cosine. If you see the secant, what it's doing is it's going in the opposite direction. So here cosine goes up and down. Secant is going to be opposite. It's going to go down and then up. Same thing here. This goes down and up from here to here. This one's coming up and then down. So because it's the reciprocal, it's going to be going in the opposite directions. So this one's going to go up. This one's going to go down. That one's going to go down. There we go. And so my light blue, that is my secant graph. Algebraically explain why the secant function fails to have any x-intercepts. Because 1 over cosine x will never equal 0. It can't happen. So, using our graph above, let's answer these questions. Which of the following represents the period of secant x? Well, our b is a 1. So we would have 2 pi over 1, so our period would be 2 pi. Same rules as all the other ones. Which of the following could not be the value of secant? Well, if you notice, secant is never between 1 and negative 1. It's never in there. Ever, ever, ever. So any values between 1 and negative 1, it can't be. So therefore, it can't be 1/2. And then consider your work with sine and cosine. Evaluate each of the following. Express your answers in exact and in simplest forms. So these are all the reciprocals. Secant 60, I want the reciprocal of cosine 60, which cosine 60 is 1/2. So that means secant 60 is 2. I just flip it. Cotangent is the reciprocal of tangent. So tangent of 150, that would be in quadrant 2. My reference angle would be 30. So this would be -3/3. So if I flip that, I have to rationalize. I would get -3 radical 3/3. So those reduce. And it's negative radical 3. Cosecant, that means I'm looking at sine. This is going to be of 135 if I turn it from radians into degrees, which I like to do because that's the way I can see it easier. 135 is quadrant 2. Sine is positive in quadrant 2. Again, remember, all schools torture children. So sine is positive there. Reference angle is 45. So the sine of 45 is radical 2/2, and I need to flip that. So I'm going to multiply top and bottom by that, reduce it, and I get radical 2 for that. So you got to remember with those reciprocals, you have to keep flipping. Next one here, trying to draw the graph of cosecant. It's very similar to the graph of your secant. There's going to be asymptotes. Wherever sine is a 0, we are going to have an asymptote. So that's going to be at -2 pi, -pi, 0, pi, and 2 pi. So asymptote, 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 and asymptote. So those are where our asymptotes are going to end up being. So what will be true of these values? They are undefined. Wherever sine is 0, it's going to be an undefined value for your cosecant. And cosecant is going to be going in the opposite, much like your secant. Cosecant will never be in between 1 and -1. It's just not going to happen. So which of the following represents the period of cosecant x? That's going to be 2 pi. That's in the standard period. How many solutions are there where cosecant equals a 2? I'm going to draw 1, 2, 3, 4. There is 4 of them. Excuse me. If drawn in the same set of axes, the graph of y equals cosecant would not intersect which graph? Again, those are verticals, so not even an issue here. It cannot intersect anything for your y values between 1 and -1, so it would not intersect at y equals 1/2. And then if A is an angle whose terminal ray lies in the 4th quadrant, cosine is 1/3, so I'm going to start drawing myself a picture. Here's my angle, cosine is 1/3. Determine the exact value of cosecant theta. So I first got to find my missing side using Pythagorean theorem. 3 squared is 9, minus 1 gives me 8. Square root, being in quadrant 4, I want a negative, so x is -2 radical 2. So sine would be -2 radical 2/3. Cosecant means I need to flip that. And then I need to rationalize. I can't leave radical 2 in the denominator. So that's -3 radical 2/4.